Hello and welcome. Today, we have a fantastic geometry puzzle that looks tough at first, but has a beautifully simple solution if you make one clever move. Here's the setup. We have a square, ABCD, with an equilateral triangle, AFE, fitting inside. One vertex is fixed at corner A. The other two vertices, F and E, touch the sides BC and CD. We are only given the area of the small triangle FCE. The challenge is to find the area of the triangle on the side, ABF. I encourage you to pause the video now and try to solve it on your own. All right, ready? Let's begin. First, let's break down what we know. The triangle AFE is equilateral. This means its sides, AF, FE, and AE, are all equal. Also, because its vertices E and F touch the square's sides symmetrically, the distances CE and CF must be equal. This makes our new triangle, FCE, an isosceles triangle. Since the angle at C is a 90-degree right angle, the other two angles must each be 45 degrees. A 45-45-90 triangle is essentially half a square. Because of this, if we draw a height from point C to the side EF, its length will be exactly half the length of EF. Keep that in mind. Now, for the other two triangles, ABF and ADE. The corner angle of the square at A is 90 degrees, and the equilateral triangle's angle is 60 degrees. This leaves a total of 30 degrees for the two remaining angles, FAB and DAE. Due to symmetry, these triangles are congruent, so each of those angles must be 15 degrees. So, how do we proceed? Here comes the creative trick. This is the move that solves the puzzle. What we have to do is rotate triangle ABF 90 degrees counterclockwise using point A as the anchor. This creates a new identical triangle. This rotation merges the two 15-degree angles to form a new larger triangle, GAE, with an angle at A of 30 degrees. Now, let's draw a perpendicular line from point G down to the side AE. We'll call this line segment GH. This is the height of our new triangle, GAE. If we look at the small triangle AGH, we have a 90-degree angle at H and a 30-degree angle at A. This means the last angle is 60 degrees. Now you can recall the 30-60-90-degree triangle rule. This rule states that the side opposite the 30-degree angle is always half the hypotenuse. In our case, the height GH is opposite, so the height GH is equal to the hypotenuse AG divided by 2. Now, let's put it all together. We know AFE is an equilateral triangle, so all its sides are equal, and our rotation made AG equal to AF. Therefore, AG, AE, and FE are all the same length. We just found that the height of triangle GAE is AG divided by 2. And earlier, we established that the height of triangle FCE is FE divided by 2. Since AG and FE are the same length, the areas of triangle GAE and triangle FCE must be equal. And there it is. That's the key. The area of our merged triangle, GAE, is simply the sum of the two triangles we started with, ABF and ADE. Since those two are identical, the area of triangle ABF must be exactly half the area of triangle GAE. Therefore, the area of triangle ABF is half the area of triangle FCE. Then the area that we were looking for, ABF, must be 4 divided by 2, which equals 2. A beautiful solution, isn't it? If you found another way to solve this puzzle, please let me know in the comments below. I'd love to see it. For more fun problems like this, please consider subscribing to the channel.